Now we're going to be looking at sketching quadratics. So remember, the graph of a quadratic has a parabolic shape that may open upwards or open downwards. Another key feature of this shape is if it opens upwards, we have a minimum vertex or turning point in the graph. If it opens downwards, we have a vertex that is a maximum. So here we see a maximum y value for this graph. Also, we'll always have a y-intercept for our parabolic shape. However, with our x-intercepts, we could have 2. We could have 1, where it just touches the x-axis, or we could have 0. The last key feature of our quadratic is this axis of symmetry. So there we see this line of symmetry, which could be described by a line, say x equals 3, so a vertical line. And that symmetry means if we reflect in that line, a point we might see over here will also be on the graph if it is reflected in that line, meaning that these two distances here from our line of symmetry is the same. Now, the general form of a quadratic is given by y equals ax squared plus bx plus c, where a, b and c are constants. The quadratic term, ax squared, is the dominant term. This tells us the shape of the graph. So if a is greater than 0, that is, if a is positive, then we have a graph that opens upwards, producing a minimum vertex. However, if a is negative or less than 0, then we get a parabola that opens downwards, giving us a maximum vertex. The plus c, just like in our straight line equation, gives us the y-intercept. However, if we want more information, we need to go to the factor form. So in general, if we can factorise this expression here, it'll factorise as a bracket x take p times x take q, where p and q are also constants. Again, a tells us the shape, but now the values of p and q give us the x-intercepts. Note that if the parabola does not touch or cross the x-axis, we cannot write it in factor form. So both of these forms are useful. The general form easily tells us the y-intercept and the shape. In factor form, we easily see the x-intercepts and the shape. So I'll see that when we're sketching, we'll use both forms. Now let's look at an example. Here we have y equals x squared, take 3x plus 2. If we factorise this expression, then we get y equals x minus 1 times x minus 2. Now let's go through the key features. First, our shape. I can tell that it opens upwards here, giving us a minimum vertex because my dominant term, the x squared, has a positive coefficient. Here it's just 1. Second, the y-intercept is when x equals 0. So to show this clearly, I'll sub 0 into my expression for x, and I'll see that I get y equals plus 2. So again, the y-intercept can be read directly from this form. Now the x-intercepts are when y equals 0. So you can see now when I substitute in y equals 0, it is best to use the factorised form because now I can use the null factor law. The solutions to this equation are when I make the first bracket 0 by the value x equals 1, or when I make the second bracket equal to 0 with the value x equals 2. The next key feature is the vertex. So to determine where the vertex is, we need to exploit the symmetry of our quadratic. So if it has the x-intercepts of 1 and 2, we'll find that the vertex must lie halfway between those 2 points. To find that halfway point, we add the two x-intercepts together and divide by 2, giving us a value of 1.5. So we know that the vertex, or the turning point, is occurring when x equals 1.5, but we don't know the height, or the y value. To find the y value of the vertex, we simply sub in x equals 1.5 into either form and calculate. Here we get -1/4. So our vertex is the xy coordinate, 1.5 -1/4. So here's my sketch of the equation y equals x squared minus 3x plus 2. So I see my y-intercept of 2. Clearly I see the shape of my parabola, the x-intercepts of 1 and 2. So here our turning point, it is much more clear when we look at the sketch that the turning point is halfway between my x-intercepts. That's because our line of symmetry must be equal distance from 2 and 1. So that's why we were able to complete this calculation to find the number halfway between 1 and 2. To do so, we simply add them and divide by 2, like taking the average. Then we knew our parabola was turning around somewhere on this line where x equals 3 on 2. But to find out where it was turning around, we simply had to sub that value into our equation. Doing so gave us -1/4. So remember here that a sketch is rough. There's no need to precisely plot out values. You might see here that my scale along the x-axis is a little bit dodgy. This looks more like perhaps 3 if I was using a grid, but I was pretty happy with this shape here. Okay, so a nice shape is much more important than an overly precise scale. So when you're sketching your quadratics, it can be a good idea to not put the points in first. Get a rough idea of where they might be, where you want to go through on your graph, and then sketch in your quadratic. Then you can go back and precisely put in the key features. Let's have a look at one more example. Here we have y equals -x squared plus x plus 12. So first of all, the shape. Here the parabola opens downwards because my value of a, the coefficient of my dominant term, is less than 1, giving us a maximum value here. The y-intercept is when x equals 0. I can see that's 12. To solve for the x-intercepts, I need to sub in y equals 0. So here, that gives me the equation 0 equals -x squared plus x plus 12. So I need to factorise to solve here. So I can use the null factor law. I could go through and use the general quadratic equation, however that would take too long. Now, when you're trying to factorise, I find it really annoying when I have a -x squared term. So the first thing I did here in solving this equation was to multiply through by -1. So that changes the sign on each term, giving me positive x squared minus x minus 12. Now factorising here, it factorises as x plus 3 and x minus 4, giving me solutions of x equals -3 or x equals +4. Note that if you need some more practice at this step, really important that you do so. Otherwise you won't be able to sketch your parabolas. Next, the vertex or the turning point. So that's occurring halfway between my two x-intercepts. To find that point, I add them together and divide by 2, giving me x equals a half. So a dodgy little sketch here shows my two x-intercepts, my y-intercept of 12, and what I figured out here was that my parabola is going to turn around at x equals a half. So the vertex is somewhere on this line, but to figure out exactly where it is, how high it is, I need to sub in the x value of a half into my equation and solve. Here I get 12 and a quarter. So my vertex is at xy equals a half, 12 and a quarter. Now here's a slightly better sketch. I'm showing my two x-intercepts, my y-intercept of 12 and my vertex, and I'm labelling the graph. So this one here, I got a bit confident with my first one looking so good. This one is a little bit wonky. So here I think I labelled these points and tried to go through them rather than just trying to get a nice shape with the vertex roughly at x equals a half. Okay, so now it's your turn to have a go at sketching. However, when you're sketching these ones initially, you'll only be looking at a value of a as plus or minus 1. This will make it a lot easier for you to factorise and find the x-intercepts. And the ones you have a go at today will all factorise nicely. So looking at the key steps, first determine the shape. To determine that, you look at the dominant term, the x squared term. Next, find the y-intercept. That's when x equals 0. Next, find the x-intercept. That is when y equals 0. Remember, to do this step, we need to use our skills from our first unit of the year. We need to factorise our quadratic and then use the null factor law. Next, we need to find the vertex, or the turning point. To find where that occurs in x, we average or add our two zeros, x-intercepts, together and divide it by 2. Then we sub the value for x we get out of that into our equation to find the y value.